Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Zahira. My group members are Atifa Zuhaira and Aina Biha. So today we're going to present about the Fabry Perot interferometer. Firstly, what is an interferometer? An interferometer is an instrument for making precise measurements for beams of light of such factors, which are length, index of refraction, and wavelength determination. So basically, interferometer divides a beam of light into a number of beams that transmitted across different directions. Interference in interferometer occur when two waves are superimposed with each other. Then the interference appears as a pattern of light and dark bands called the interference fringes. Next, a short introduction of Fabry-Perot interferometers. The Fabry-Perot interferometers or the Fabry-Perot resonator is an interferometer of great importance for laser analysis. It is often used as a high-resolution optical spectrometer. It is also was produced by the French physicists, which are Charles Fabry and Alfred Perot in 1897. And then multiple reflections of light in the interferometer will form very narrow and sharp fringes. Okay, next, working principle of Fabry-Perot interferometer. Okay, first of all, the Fabry-Perot interferometer is based on the principle of multiple reflection. And a typical Fabry-Perot interferometer consists of two reflective mirrors, which one plate remains fixed, the reference mirror remains fixed, while the other plate is movable on an adjustable screw. And the inner surface of these two mirrors are coated with film of high reflectivity. The blue region here is the film. In such a way, they enclose a plane parallel plate of air. And then both mirrors are aligned parallel to one another at a distance d, that forming a reflective cavity. So the separation region here is referred as the cavity. And then this instrument initially works when a monochromatic light from the laser source is allowed to pass through the mirrors with respect to an optical axis at an angle of incident theta. So this is the incident theta. As a result of that, multiple reflection will take place inside the cavity. So we can see here, inside the cavity, repeated reflection occur. So when light pass through the second plate, they will focus by a converging lens here. Then the emerging set of light are brought together at some point P on the screen. Finally, destructive and constructive interference occur on a screen in concentric circle. This is the circular fringe pattern, and then the larger the fringe contrast, the better the cavity.
Next, we proceed with question 2, which is the spectral resolution using Fabry-Perot interferometer. Fabry-Perot interferometer has a high spectral resolution. This is because when the light hit one of the two surfaces of partially silvered glass plates, some of the light will transmitted out, producing the multiple rays that will interfere with each other because they are out of phase, and then the remaining light will reflected. So the huge amount of interference rays will produce the high spectral resolution for Fabry-Perot interferometer. So here we can view the equation for the resolvent, which is lambda over change in lambda equal to m pi r over 1 minus r square. So when we rearrange the equation, we can get the equation of the shortest distance between the two spectral lines, which is change in lambda equal to lambda 1 minus r over m pi sub r. So from the equation, we can prove that the two wavelengths satisfy the Rayleigh criterion. Rayleigh criterion states that two images are just resolvable when the center of the diffraction disk of one image is directly over the first minimum in the diffraction pattern of the other. So here we can see the equation for the Rayleigh criterion, which is angle is equal to the 1.22 lambda over d, where we can define d as the diameter of the lens. So we use this formula because it indicates the smallest possible angle between point sources or the best resolution. So from the equation, to get the better resolution, we must use the shorter wavelength so that it will reduce the angle, because the smaller the angle, the better the resolution. Thank you.
Next, I will explain about the latest application of Fabry Perot mechanism. Because of the ongoing pandemic, many researchers joined forces to develop a self-test kit which applied a high-contrast probe cleavage detection (HCPCD) mechanism by using porosilicon interferometer sensors. Researchers from a United States biosensor company called Scifox collaborate with other academic institutions to initiate a study about HCPCD mechanism by using porosilicon interferometer. They found that HCPCD mechanism can be applied to develop a disposable self-test kit of COVID-19. This test kit helped to manage COVID-19 cases in more organized way and also cut the cost and time spent for the application process in order to detect the presence of virus. It also helped to minimize a false negative diagnostic due to the sensor not detecting the viral RNA in the sample because of its detection limit. Thus, sensitivity, accuracy, and also instant pathogen testing can be fulfilled through the HCPCD, that is known as sensitive diagnostic tool, based on the extraction of probes from the surface of photonic biosensor. Working principle of porosilicon interferometer is thin film interference. Fabry Perot reflectance fringes are applied when the reflections of light occurs from the top layer to the bottom layer, then they interfere with each other. Effective optical thickness will determine locations of fringes and periodic of interferometric pattern. This is because large amount of molecule inside the pores causing a large changes of shift. The size of pore must be bigger than molecular target, and molecules will in the process of surface functionalization to provide plenty of space for infiltration. Porosilicon layer refractive index increases when molecular species infiltrate the pores. For HCPCD, high index biotin dsDNA Q dot probes are used to functionalize the porosilicon interferometer, causing reflectance fringe redshift. A blue shift happens when the Q dots is removed due to the cleavage of DNA catalyzed by an enzyme. Even though redshift is known as a biofouling induce that cause a false positive detection, it can be avoided because blue shift depends on the size and materials of the probes. The degree of reflectance shift is proportional to the amount of material entered or withdrawn from the pores, and the fringes shift correlates to the change in phase shift. Thank you.